Hello and welcome to this month's edition of Sci Cam, the online science magazine show. I'm Michael Contario, and joining me this week is my guest, Robin Lamble. Hi, Robin.
Hello.
So, Robin, you're going to start us off this week with a look into basically the area that you're currently researching. Can you tell us a little more about that, please?
Yes, I research solar power. Now, you may have heard in the news recently that Germany is producing half of its energy by solar power. This is not exactly accurate. It's only occasionally true for a few hours at a time. On average, solar power is still not that huge an issue. But what we are seeing is an enormous growth in the amount of solar power. What we've seen over the first half of this year is that Germany is producing one-third of its energy from renewable sources. Um, those still primarily are wind or biomass, so that's burning plant matter for energy, which is still renewable because, of course, you can grow more plants and they take as much carbon dioxide out of the atmosphere as they put back in when you burn them. But what we're seeing is that those two are doing well, but solar power is growing particularly strongly considering its initial size. In fact, worldwide it's growing by about a third per year, and it's been doing this quite consistently now for over 40 years, so really quite a positive trend. It's also worth bearing in mind that things like wind do do better in the winter, when of course it's windier but not really so sunny. Um, so hopefully we'll have more good news from solar power to come from. But it's just a good landmark to see that actually solar power really does have the capacity to power a nation, as it were. So as renewable energies have grown, we have seen a decrease in the amount of coal that needs to be burnt. It was often assumed that you'd have to basically keep the same amount of coal going anyway, just because solar power is a little bit variable, but between all the different types of renewable energy, you do see a good positive trend of stabilization of the power grids with a bit of engineering. But I thought I'd just give a brief overview of how silicon solar cells, which aren't actually the type I study, but how they work, because they're the most sort of fundamental one, the one that you see as you're sort of walking around. So the thing about silicon is it's a semiconductor. So you've got normal conductors, which is where electrons can move around at will. Then you've got insulators, which is where the electrons are basically stuck. But silicon and semiconductors basically have a bunch of electrons in the lower energy level, and in this energy level, there's basically no space for them to move. Then you've got a gap where there aren't any energy levels for the electrons to be in, and then you've got a higher gap, a higher group of energy levels, but it's because of the energy gap, there aren't really very many electrons in here. So if you want a current to flow, you need to have electrons in the upper group of energy levels, or you need to make some space in the lower group of energy levels. And if there are any gaps in the lower energy levels, then actually what you can do is have an electron move into the gap. Now you've got a gap over here, so an electron can move into that gap, and basically you can follow the gap as it moves around, and it moves around exactly as though it were a particle with a positive charge, the opposite charge to an electron. So we call this a hole, and it also contributes to the current. So what we've got here in our silicon is what we do is we add other different types of atoms to the silicon. These are impurities or dopants. And these are things like silicon, but have one extra electron or one less electron. And basically they'll throw out that electron or steal an electron from the rest of the silicon, which then adds either an electron to the upper energy group or takes out an electron from the lower energy group. Now, if you have two different types, two bits of silicon with different levels of impurity, then the electrons will move from the one place where there are too many of them thrown out by these types of impurities to another place. And this sets up an electric field. Now what happens is you just wait for some light to hit your solar cell. The light will kick an electron out of the lower band into the upper band. Now this electron in the upper band then sees the electric field and is convinced to, on average, go in one direction. It'll in fact keep going in that direction. It'll push electrons that are already there further along, and they'll start a chain reaction all the way around a circuit. And of course, this chain reaction of moving electrons is exactly what we call electricity, which is what allows us all to see each other over the computer and do absolutely everything in modern life. So that's how solar cells work.
Thank you very much for that, Robin. You said that when you got those, you get the electrons kind of causing a chain reaction of other electrons. Can you give us a little bit more detail about how that happens? Does one of them just like smack into another, and is it like billiards, or is there more to it than that?
Well, I mean, it's going to depend a lot on the system. So basically, electrons all repel each other because you've got this charge going on. But generally, they can sort of, you don't have to worry about what individual electrons are doing. You can treat it as a sort of general wave of motion traveling around a circuit, rather than sort of worrying about, okay, you've got one electron here and it hits an electron here and sort of causing a very billiard style type of motion. It's much nicer to think about it as being a smooth transition, because of course all the electrons know where the other ones are in some sense, because they're reacting to each other, and by and large they'll move continuously unless they bang into a stationary atom. The quantum mechanics of it is quite nice. So as long as you've got a nice sort of crystalline material, everything can move quite smoothly around.
Well, yeah, thank you very much for that. If you've got any other questions that you'd like to ask Robin, you can put them in the comments on the YouTube page that you're watching, or you can put them in the comments on the Google Plus Watch page if you're watching there. But in the meantime, I'm going to start by talking a little bit about gravity and weightlessness and what all these have to do with Einstein's theory of general relativity. Because one of the things that we love about space is how when you've got astronauts up in the space shuttle or just actually anyway orbiting the Earth, whatever they're in, they're obviously weightless, and you see them floating around. Chris Hadfield sent down some marvelous videos from the ISS of what happens and how you have to deal with life in those sorts of situations. And NASA seem to have actually kept that running. So do check those out if you get a chance, and they're all over YouTube. But why are they why are they weightless? Because if you actually look at the distance away from the Earth, the ISS only orbits about 400 kilometers above the surface of the Earth, which is much, much closer than the Moon, say, orbits us. And obviously, we can feel the effect of the gravity of the Moon. Well, we don't feel it. We see it in the tides, and we also know that the Moon orbits the Earth because the gravity of the Earth is pulling it in. So why are they seeming to be weightless? And it's actually because all of the astronauts in their spaceship are all constantly in free fall. They are actually all still being pulled towards the Earth by the force of gravity. It's just they're going so fast, sideways effectively, that even though they're getting pulled towards the Earth, in the same amount of time as they're moving towards the Earth, they're also moving sideways past it. And so they end up just in a circular orbit going around rather than crashing into it. And this leads us to something that's actually one of the things that got Einstein to think about gravity in the way that he did, which is that if you're in free fall, you can't actually tell the difference between being in free fall, being pulled by gravity, and being just somewhere where there was no gravitational field at all. Obviously, that's actually really hard to come by because gravitational field of everything just keeps going effectively. It gets weaker and weaker and weaker, but it goes as 1 divided by the distance away from the center of mass of that object, which is the point where we can think of all its mass being concentrated on its weight acting. 1 over that distance squared. So as you double the distance away from that, the gravitational field becomes a quarter of the strength. In fact, if you look at the ISS and work out what the gravitational field strength is there, it's actually not a huge amount less than it actually is here on the surface of the Earth, because the radius of the Earth is so much bigger than the extra distance that you have to go up to actually get to the ISS. But if you were in a completely weightless, completely gravitationally free environment, that would feel exactly the same as being in free fall towards something that's pulling you through the force of gravity. And Einstein kind of actually went a bit further than this, and he came up with something called the Equivalence Principle, which says that experiments that are performed while in free fall will come out exactly the same as if they were just somewhere entirely stationary, and so you can't tell whether or not you're being accelerated by gravity or not. So the way to think about this is, imagine just like, say, throwing a dart. Here on Earth, if you throw a dart, you'll see it curve downwards. You actually have to throw it slightly upwards if you want it to land, hit the dartboard at the same height at which you threw it. But if it was somewhere that there was no gravity, you could just throw the dart exactly straight and it would just go straight into the bullseye. But if you were still on Earth, but you and the dartboard were falling with no air resistance, obviously that's not possible, but if there was no air resistance, you'd both be falling with the same acceleration, and you could just aim directly at the bullseye, and to you it would seem as if the dart just went straight forwards and hit the bullseye. Whereas to anyone just standing on the surface of the Earth, you could see that you were falling, and so was the dart. It was falling in exactly the right way to hit the bullseye. So that's the equivalence principle, and this made Einstein think that maybe the force of gravity wasn't quite like the other forces. Maybe it wasn't really even a force at all. And in the General Theory of Relativity, he actually thought, what happens if it's not a force, but it's instead a warping of space-time? So that even when there's gravity, we can think of things going in straight lines, which is what we expect them to do when there's no force on them. It's just that the thing that we're effectively drawing those lines on isn't a nice flat surface. Okay, so when I say surface, we're talking about things in more dimensions here, so it's quite confusing, but you've kind of almost seen something like this in 2 dimensions before. Because if you look at a globe, when you've got all the surface of the Earth on a globe, you can draw a line between 2 different points and say that's the quickest way across the globe around it to actually get to that place, and it's actually what's called a grand circle, and it's generally how aircraft will try and fly if they're going on long journeys. But if you had a map of the Earth and tried to draw a straight line between the same 2 points, you'd actually, if you actually followed that line, you'd end up going a different distance, because you've got the space curved in the case of the sphere, and you've got it straight in the case of a map. You can't actually really map those 2. And so when you're going from one to the other, you're actually kind of deforming the space and squishing it and squashing it and turning it into a different form. And you know this because you can't just cut open all the paper on the surface of a globe and just have it as a nice flat piece of paper. You'll get it just not working. It'll either bunch up or you'll have to cut it more and then it won't join up. So those 2 spaces are different. And Einstein's theory of relativity, general theory of relativity, actually said, well, what about all this if all this mass is just bending space and time? So what we think of as a straight line isn't. And instead particles follow these straight lines in this warped space and time, these lines are called geodesics. And so we use that to actually put together this theory. And it works, and it also nicely explains why light would bend around distant galaxies, and you can get gravitational lensing, because the light's still really traveling in a straight line. It's just that the straight line looks wonky to us because we're not seeing the space in the same way. And so this actually also leads to interesting effects, because in special relativity, Einstein had already linked space and time. And when he put gravity into the mix as well, he showed that gravity not only warped the space, but also time as well. You may have heard of this before as to thinking when you're falling into a black hole, to people outside, you just kind of get slower and slower and slower as you're being pulled in your time until it seems to stop for people outside. And that's another consequence of this warping of space and time by the ridiculously huge mass of the black hole. But there are a couple of little wrinkles to this, in that the equivalence principle, which I mentioned before, which said that the experiments are the same whether they're stationary or with no gravitational field nearby, or in free fall inside a gravitational field, is that the experiments have to be really small, because otherwise they'll experience what we call tidal forces. And these are pretty much what they sound like. They're forces which are different on different positions, which are both a similar distance away from a mass which has got a gravitational pull, like the Earth or the Moon, but they're a sufficiently different distance that the force is slightly different, and so things get pulled apart. And so this is one of the things that, well, this is basically how the tides are caused, because the gravitational pull of the Moon on different sides of the Earth is different. So it's stronger on the side nearest it, which pulls the water up, and so you get a strong high tide there. Whereas on the other side of the Earth, there's actually a different distance. There's actually a difference in the force of gravity from the Moon acting on the water effectively at the top of the sea and lower down. And so that's actually getting stretched out as well, because the force is stronger on the bit of water that's closest to the Moon and weaker on the bit of water that's furthest away from the Moon. So you end up with basically a stretching force, so that's why you get a high tide on the opposite side of the Earth as well. And of course, we need to make sure that there's no air resistance or anything that's going to get in our way, which we do in free fall here. So I think that's a nice idea, that you can look at how astronauts move in the space shuttle, the space station, and just think that the fact that they move like that gave us one of the most powerful and incredibly well tested, crucially, theories of the 20th century. I mean, we tested it so much. I mean, even GPS, the clocks which are on the GPS satellites run at a different speed to atomic clocks on Earth, and this had to be taken into account, and this has been tested to ridiculous accuracy. And so the time signal that you receive from these satellites actually matches the local time on Earth. So there you go, Einstein's theory of general relativity from freefall. So I'm just going to quickly check whether we've got any comments on here, any questions have come through. While I'm doing that, I'd also like to say that we've got a new Sci Cam blog, which every Tuesday that we're not having a live show, we will update with a new blog post. Over the past month, we had a welcome post, a post about how nerves grow inside the body. We've had a post about hearts, and we've had a post about perceptions of physics. So we've got a huge variety, but lots of different topics, and they'll keep on going. So you'll be able to go to www.contrarythoughts.com and look at www.contrarythoughts.com/sci-cam. There we go. And look at the blogs there, and feel free to comment, ask questions. All the people we've got will be more than happy to answer any further questions that you've got. And in fact, we've got a question here for Robin, which is from Jens Renneking, who's I know has asked a few questions on this show. Good to see you again. And so he asks, what is the efficiency of solar cells at the moment? How has it changed in the past? And is it expected to rise in the future? And if the efficiency has changed and will change, how is that achieved? So, Robin.
Okay, yes, so basically the solar cells that you can buy off the shelf at the moment are about 20% efficient. Now, that might not sound like a terribly high number. That means that of the amount of sunlight hitting them, only 20% of that comes out as electricity. There's actually a thermodynamic limit on how efficient solar cells can get from the conventional architecture that we've got at the moment. That would be 30% efficient, really. There's most of the solar cells that I work on are only a couple of percent efficient, and so things like satellites, however, So I described having two different energy levels, the lower level and the higher level. If you have this set up, you can only get 30% efficiency. If, however, you've got lots of different energy gaps between lower levels and higher levels, you can get much more energy out from each bit of sunlight. So for things on the space stations, on satellites, they want to have much higher efficiencies, and if you've got the money for it, and you want to keep as little space as you want, as you can for solar panels, you can get into the 40s. So on satellites nowadays, you've got 44%. Well, we have made ones which are 44%. These are incredibly expensive, so you won't see them on anyone's roofs, but we can make them if we want to. So efficiencies over time, well, yeah, they've been going up quite a bit. So you can quite easily now make 25% efficient solar cells. That's nearly your lot. Probably solar cells won't ever exceed the 30 mark, which is quite close to the thermodynamic limit anyway. A lot of what we will probably see is an increase in the amount of solar cells that are cheaper to make but not necessarily more efficient, or we might see increasingly concentrators. So because at the moment the thing about solar power is it's all driven by economics rather than by what we can actually do as scientists. You know, if you want to cover the entire world in solar power, you can do that. You can generate limitless energy. But more of the time, you've got the problems of how much roof space do we have versus how much money do we want to devote to this. So quite possibly we'll see concentrators coming in. This is where instead of having everything covered in solar panels, you cover everything with lenses or some form of plastic that will conduct light or change how light is moving, and then a little solar panel. And then the little solar panel might be one of the really good ones that you'd put on satellites, and it's collecting light from a huge area that all comes towards the same place. And in this way, you can get what is effectively pretty high efficiencies, but without having to pay for covering a large area with those really high efficiency solar panels. So yeah, hopefully there will be some progress, but actually for the sorts of solar panels that you're going to get, 20–25% is probably about as far as we're going to be.
Oh, thank you very much, Robin. Jens, I hope that's answered your question. And I'd just like to add one more thing about the equivalence principle that I meant to mention before and managed to forget, which is that as well as things always feeling the same, whether they're stationary with no gravitational field or in free fall with a gravitational field, you also have an equivalence between standing on like the ground in a gravitational field or being somewhere where there's no gravitational field and actually being accelerated upwards. So if you imagine being in a lift, which you can't see out of on Earth, if that was stationary, then when you looked at a lift inside a rocket ship with a rocket booster pushing it along, you would stand effectively on the floor of that lift in the same way. And this is actually why when you have space stations in sci-fi, you quite often see the ones which are basically rotating rings, like in, say, the video game Halo. And what happens here is you're actually being accelerated towards the center of the ring by its spinning, and for you to actually not just go flying off through the floor, the floor needs to push you in. And basically that acceleration into the center feels to you as if there's gravity holding you on the outer edge of the ring. So this is the outer edge of the ring, you're standing there, being pushed up by the floor towards the center, and if you've got get the speed right and the radius right, then it could feel just like normal Earth gravity. So you wouldn't have to worry about that. Of course, if you're in space, you don't have to worry so much about the fact you've got a giant rotating ring. So, which is why sci-fi likes that sort of thing. So I think that's everything. Jen says thank you for the foray into the economics of solar power as well. So thank you very much for that, Robin, and thank you just in general. And yes, we'll be back with another live show in just over a month. I believe it's going to be it's always on the second Tuesday of the month, so that'll be the 12th of August next month. And every Tuesday until then, go to www.contrarythoughts.com/sci-cam or weekly blog posts. Thank you very much and good night.